Welcome back. Now we know that circular motion is necessary for the rotational motion. So now we have to study about the relation between linear velocity and angular velocity. Now here we have to consider a particle which is moving along the circumference of circle of radius r in the anticlockwise direction. Now suppose particle moves from point A to the point B in a short interval of time del t. Now in this time the particle cover the distance is equal to the length of the arc AB, and which is denoted by del S. And during this time the radius vector rotate through the angle del theta at the center of the circle. Means del theta is the angular displacement. Now here note that as time is very small, so the arc AB is considered as a straight. Means the AB, the segment AB shows the linear displacement. The angle AOB shows the angular displacement, and R is the radius of the circle. Now vector OA and vector OB is the radius vector. Now the magnitude of linear velocity is defined as the rate of change of displacement with respect to time. So mathematically we can write here v is equal to ds upon dt. Now in a limit form, limit del t tends to 0, del s divided by del t. As we know that time goes to 0, means which is very small. Now we know the relation between linear displacement and angular displacement, that we already studied, and so del s is equal to r into del theta. Now we have to put the value of del s in this equation. So we get here v is equal to limit del t tends to 0 r del theta divided by dt. Now here note that here del s is replaced by the quantity r del theta. Now r is the radius of the circle which is out of the limit because it is constant, and so v is equal to r in bracket limit del t tends to 0 del theta divided by del t. Now after evaluating the limit, here we get v is equal to r and in bracket del theta divided by d theta divided by dt. Now we know that the rate of change of angular displacement with respect to time is called as angular velocity according to our definition. And now here we get v is equal to r omega. Means this is the relation between linear velocity and angular velocity. Angular velocity denoted by omega and linear velocity denoted by v. So v is equal to r omega. Now we know that the direction of angular velocity along the axis of rotation and the direction of linear velocity is along the tangent to the circular path. So this linear velocity is also called as a tangential velocity. Means this is the relation between tangential velocity and angular velocity. Now in a vector form we can write vector v is equal to vector omega cross vector r by using the right hand rule. So in this way here we are to give the relation between linear velocity and angular velocity. Means angular displacement in a circular motion is analog to the linear displacement. Same like that angular velocity is analog to the linear velocity. Now next one, here we have to derive the expression for the resultant linear acceleration in a non-UCM. Now we know that in a non-UCM the linear velocity changes due to both change in magnitude and change in direction of the velocity. Means here linear velocity changes due to both in magnitude and direction, because we know that in a non-UCM the magnitude of linear velocity, that is the linear speed, which is a variable, and again the direction is always the changes in a circular motion. So again note that in a non-UCM, linear velocity changes due to both in magnitude and direction also. So now here we have to already give the relation between linear velocity and the angular velocity, that is vector v is equal to vector omega cross vector r. So now here we have to differentiate this equation with respect to time. Then we get here ddt of vector v is equal to, now here we have to apply the product rule. Now first vector omega cross ddt of vector r plus ddt of vector omega cross vector r. Now here note that vector dr divided by dt, r is the radius, means it is the distance, means ddt of distance, and here we get a linear velocity, means in shortcut dr divided by dt, it gives the linear velocity. Again we know that the rate of change of angular velocity is called as angular acceleration, and again the rate of change of linear velocity with respect to time is gives the linear acceleration. So vector a is equal to dv divided by dt, vector alpha, that is angular acceleration, is equal to d omega divided by dt, and the linear velocity is dr divided by dt. By putting this value we get a vector a, that is the total linear acceleration. Total linear acceleration is a non-UCM. Vector omega cross vector v plus vector alpha cross vector r. So now here note that dr upon dt, it gives the linear velocity, and d omega upon dt, it gives the angular velocity. And so this equation can be written as total linear acceleration is equal to vector ar plus vector at. So now here note that the vector omega cross vector v, this product, that means the direction of this product is along the radius and towards the center of circle. So this is the radial component of total linear acceleration, which is given by vector ar. So now here note that direction of linear velocity is along the tangent, direction of angular velocity is along the axis of rotation, and the direction of radial acceleration is along the radius and towards the center. And so we can write vector ar is equal to vector omega cross vector v, means this is the radial component of total linear acceleration. Same like that, the direction of this cross product, that is vector alpha cross vector r. So here it is along the tangent to the circular path. The direction of radius vector is along the radius and away from the center of circle. Again, the direction of angular acceleration is along the axis of rotation, and so according to the right hand thumb rule, the direction of tangential acceleration is along tangent to the circular path. Now here we have to use the right hand thumb rule. Means this product gives the tangential acceleration because the direction is along the tangent. So here in a non-UCM, the total linear acceleration has a two component, radial component and a tangential component of total linear acceleration. As radial acceleration is directed along the radius and towards the center of the circle, and tangential acceleration is along the tangent to the circular path. So radial acceleration, here we have to show in this diagram. Radial acceleration is along the radius towards the center, and the tangential acceleration is along the tangent to the circular path. Means as vector ar and vector at are mutually perpendicular, and so here we have to complete the parallelograms, and now by using the law of parallelogram, the magnitude of the linear acceleration. So now here the magnitude of linear acceleration is shown by the diagonal or the total linear acceleration in magnetic direction shown by these diagonals of the parallelogram. So the magnitude of linear acceleration, we know that as two vectors are perpendicular, then everyone know that how we have to calculate the magnitude of that resultant vector. So the magnitude of linear acceleration, that is a is equal to square root ar square plus at square. And again the direction of linear acceleration with the radius, direction of linear acceleration with the radius is denoted by the symbol beta, and so beta is equal to tan inverse of at divided by r. Means we know that the y component divided by the x component, means beta is equal to tan inverse of at divided by r. Now here everyone know that in a circular motion, we know that angular velocity is constant. As angular velocity is constant, it does not change it, so angular acceleration is 0. As angular acceleration is 0, and so we know that the tangential acceleration is given by vector alpha cross vector. As alpha is a 0, so this tangential acceleration is a 0. Means in a UCM, tangential acceleration is not produced, and so by using this relation, vector is equal to vector ar plus vector at. Now in a UCM, at is a 0, means no tangential acceleration is produced, and so we can write vector a is equal to vector ar. Mean in a UCM, total linear acceleration is equal to the radial acceleration. Means in shortcut, in a UCM only one acceleration is produced, that is radial acceleration. That radial acceleration is also called as the centripetal acceleration. So now here note that in a non-UCM, if particle perform the non-uniform circular motion, so it produces the different acceleration, that is tangential acceleration, radial acceleration, angular acceleration, and the total linear acceleration. So with this we have to calculate the linear acceleration. But in a UCM, angular acceleration is 0, so tangential acceleration is 0, and so by using this equation, vector a is equal to vector ar, means in a UCM only the radial acceleration is produced, tangential acceleration is always 0. Now the next part were to be discussed in the next lecture. Thanks.